Yesterday we have seen about the electronegativity. Electronegativity is the ability of an atom to attract the shared bond pair of electrons. So the shared bond pair of electron is being attracted by an atom, and thus it represents its electronegativity. Electronegativity is like for fluorine, the maximum electronegativity was given by the Pauling, and the electronegativity for fluorine was considered to be 4. We know that as we go down the group, the value of electronegativity decreases, and as we go left to right, the electronegativity increases. Thus, we can say that electronegativity is related to the non-metallic character. So when non-metallic character increases, electronegativity increases, and when non-metallic character decreases, electronegativity decreases. This is how we can learn about the electronegativity. Then we need to know about the periodic trends in chemical properties. So when we look at the periodic trends, we first should know the periodic valence, and then we should study about the periodicity of oxidation state, and then we can understand about the anomalous property of second period element. So first let's move towards the looking at the periodicity of valence or periodicity of oxidation state. You know that valence is the property that depends upon the electronic configuration. Valence of representative elements um, can be calculated using the valence electron. So if valence electrons are n, then the valence is equal to n if n is less than or equal to 4. But if n is greater than or equal to, if n is greater than 4, then the valence is equal to 8 minus n or n. And the same way you can see that for S block element group 1 and 2, and for P block element 13, 14, 15, 16, 17 and 18, I have written the value of n. N is equal to 1 for 1, 2 for 2, n equal to 3 for 13th group, 4 is for 14th group, 5 is for 15th group, 6 is for 16th group, 7 is for 17th group, 8 for 18th group. And then we can see that if the valence electrons are 4, the valency is same as the number of valence electron. But if the number of valence electron is 5, then the valency may be 3 or 5. If the number of valence electrons is 6, then the valency may be 2 or 6. If the valence electrons are 7, then the valency may be 1 or 7. If the valence electrons are 8, then the valency may be 0 or 8. Nowadays, from oxidation state, nowadays term oxidation state is frequently used for valence. So consider two oxygen containing compounds OF2 and Na2O. We have seen that fluorine has the highest electronegativity, then oxygen, then it comes oxygen. Oxygen has electronegativity more than sodium. So in the compound OF2, we can understand that fluorine, which is having the electronic configuration 2s2, 2p5, which is more electronegative than oxygen, and that is why it is assigned -1 oxidation state, because it is more electronegative. Whereas this, we can see that in OF2 there are 2 F, so oxygen should be assigned +2 oxidation state. And this is how we can see that in OF2 there are 2 -1 F combines with +2 oxygen O +2, and this is how the oxidation state of oxygen is +2, whereas oxidation state of fluorine is -1. Now we can look into the Na2O. So into Na2O, oxygen being more electronegative accepts 2 electron, one from each of the 2 sodium atom, and thus shows oxidation state -2. So you can see that in oxygen, the oxidation state is -2. On the other hand, sodium Na, electronic configuration is 3s1, loses 1 electron to oxygen and give oxidation state +1. Thus oxidation state of an element um, is charged. Now we are going to define the definition. So you can easily understand, my dear students, that in Na2O, the oxidation state of oxygen is -2 and oxidation state of sodium is +1. We can even understand that the element in a compound which is more electronegative are assigned the negative oxidation state, whereas those elements which are less electronegative, they are assigned the oxidation state positive. Remember that the oxidation states are assigned in such a way that the overall charge on the molecule would be 0, and this is how we understand about the oxidation state. Now we can define what is oxidation state or definition of oxidation state. The oxidation state of an element is the charge acquired by the atom of an element on the basis of electronegative consideration from other atom in the molecule. Once again, the oxidation state of an element is the charge acquired by the atom of an element on the basis of the electronegative consideration from other atom in the molecule. In other words, or if I try to explain it simply, we can understand that oxidation state is the charge that will be acquired by an element when it combines with the another element which is having the different electronegativity. So due to the difference in electronegativity, some charge will be acquired by this element. This charge is known as the oxidation state. This oxidation state depends upon the element with which the element combines. Same, you can see here that in OF2, when oxygen is combined with fluorine, oxygen acquired positive oxidation state, but in Na2O, oxygen acquired negative oxidation state. Thus, the oxidation state of an element depends upon the what kind of element it combines to form a compound. So if oxygen combines with fluorine, it has got positive oxidation state, but oxygen, if it combines with the sodium, oxygen has got negative oxidation state, and thus the oxidation state changes. Periodic trends in the valence of the element as shown in the formula. Now you can see that the valence, how it can be shown with the examples of compound. For example, if you have group number 1, it always show the +1 oxidation state, and it forms the hydrides like lithium hydride, sodium hydride and potassium hydride with one hydrogen each. Same way, with +1 oxidation state, they form their oxide, and that is why you can see that two elements are needed for with the oxygen: Li2O, Na2O, and K2O. Same way, when we have group 2, the valence is +2, so CaH2, two hydrogens are required, but only one oxygen required because oxygen is -2. So MgO, CaO, SRO, BaO. Same way, when we look at the group number 13, they generally acquire +3 oxidation state. So for 2 boron, we need 6 hydrogen. For 1 aluminum, we need 3 hydrogen. Same way with oxygen being -2, we need 3 for 2. So B2O3, Al2O3, Ga2O3, In2O3. This is how we can understand. Same way for group number 14, the valence should be considered as a 4. So four hydrogens are needed with one element. So you can see CH4, SiH4, GeH4, SnH4. Same way for +4 oxidation state, 2 oxygen would be needed. So CO2, SiO2, GeO2, SnO2, and PbO2. The valence for 15 would be, let us say it is 3. So you know hydrides, for making hydrides 3 hydrogens are needed. So NH3, PH3, ASH3, SPH3. But please remember, my dear students, that here the hydrides, what we say, they are not actually the hydrides, but hydrogen here is the positive oxidation state, whereas nitrogen, phosphorus, arsenic, and antimony, they acquire the -3 oxidation state. Same way, you can see here that both the oxidation state, you can see here that in N2O3 nitrogen is +3, in N2O5 nitrogen is +5. In P4O6 phosphorus is +3, in P4O10 phosphorus is +5. In AS2O3 arsenic is +3, whereas AS2O5 arsenic is +5. In Sb2O3 antimony is +3, whereas in Sb2O5 antimony is +5. And in Bi2O3 Bi is +3. Bi generally not form stable Bi +5 compounds. Why? That we will study later on by the name of the inert pair effect. Same way, when we look at the group number 16, generally this group number 16 element acquire -2 oxidation state. So you can see that H2O, H2S, H2Se, H2Te, where hydrogen acquires positive oxidation state, and oxygen, sulfur, selenium, and tellurium, they acquire -2 oxidation state. Same way, here you can see in SO3, oxygen has acquired -2 oxidation state, and sulfur is with +6 oxidation state. The same way, selenium also +6 in SeO3, and tellurium is also +6 in SeO3. This is how we can understand about the various oxidation state. Same way when we look at the group number 17, group number 17 elements generally acquire the -1 oxidation states. So when it comes to the -1 oxidation state, the element combines with single hydrogen and form HF, HCl, HBr and HI. Same way these elements when they form the oxides, they show their +7 oxidation state. And you can see that Cl2O7, where chlorine has got +7 oxidation state, and this is how, my dear students, we can understand that in each group the valency has been remained same, and we can even see that there is an increase into the valency and going from left to right, and this is how we can understand the periodicity or periodic change into the valence of the various elements. There are many elements which shows the variable oxidation state that we will study into the other chapters, especially the transitional element and actinoids. They show variable oxidation state, and that is what we will study about them into 12th standard. Now we want to study about the anomalous property of second period elements. You know, second period elements are generally the first element in case of the group number 2, group number 13, 14, 15, 16 and 17. So these first elements